All right, now we're going to flip it around and we are going to determine the equations from a piecewise graph. So the things you want to key into is, first off, what each piece of the equation is. So in number one, these are clearly both straight lines, so linear equations. So I'm going to start off by writing f of x equals curly bracket. So there's two pieces I need to include here. Now they're both linear equations, and it looks like they change. The transition is here at x equals 2. So the first piece of my equation, so I'll call this left portion a closed circle and then a line here, is everything to the left of 2. So I'll write that transition point saying, all right, I want everything when x is less than or equal to 2. That's going to be the left portion of the graph. I'm not worried about the right one right now. So coming up with that equation, because these are both lines, we want to think about y equals mx plus b. We want to think back to our Algebra 1 days, where we have a slope and a y-intercept that we have to figure out. So the slope, now I've kind of drawn over this a little bit, but the slope of this line on the left, I can count from the transition point up 2 over 1, up 2 over 1, up 2 over 1. Going over to the left there, this is a negative slope. You read lines right, like you read sentences, left to right. That is going down, so negative 2x. And then the y-intercept is where it hits the y-axis, which I've already bolded in here at negative 1. So I say negative 2x minus 1 for x is less than or equal to 2. Great. Second piece of my graph starts an open circle here. And now again, I can count the slope of it. I'm going right one down one, right one down one, right one down one. So that's a negatively sloped line. Specifically, it's negative 1. So I can call it negative 1x or just negative x is fine. And be careful here. On the y-intercept, this graph is not technically hitting the y-axis, but you have to think where it would hit the y-axis, and that would be at 4. So negative 1x plus 4 is the y-intercept. And that's when x is greater than 2. All right, first one down. Let's do another. So again, I'm going to start off with this f of x equals curly bracket. And now I want to look at each piece. Again, on the left, it seems like I have a line. That looks like a straight line to me. On the right, notice it has a curved component to it. So this is our square root function. Now, there's some transformations that have happened to it, but this is our y equals square root of x parent function that got moved a bit. But let's do the line first because we're going to go left to right, as makes some sense. So the line on the left, I'll go green this time. I see it's an open circle here. So the transition point here is the y-axis. So in that case, that's when x equals 0. So I want the line when x is less than 0. And the square root function, I'll do in blue, is going to be when x is greater than or equal to 0. So my transition point, done. Now back to this line. So I want to again do y equals mx plus b. So the slope of this line, it looks like the next point I can find is right here that hits on a nice even coordinate point, and then there's one here too. So that's going to give me a slope. Again, it's negative 3 over 2 because rise over run, and it's a negatively sloped line. Minus 4 because that's the y-intercept. All right, great. Now, when we get to our parent function graphs, like the square root graph, we are thinking not about slope and y-intercept, anything like that. We are thinking about our transformational form, which is y equals a x minus h, square root of x minus h plus k. So I have to think, what's my horizontal shift? What's my vertical shift? And is there a vertical stretch or compression. Square root graph is based off of the starting point. So it looks like I just got shifted down 1. No horizontal shift. So that's going to be the coordinate point 0, -1. That's my h and my k. Then, if I want to figure out if there's a vertical stretch or compression, what I would do is take another point on the graph. For example, I shouldn't go green, I'll go red. This point right here. That is the coordinate point 1, 0. So what I can plug in is an x and a y value, as well as h and k, to this transformational form and figure everything out. But I am kind of familiar with the shortcut that, oh, that's a standard parent square root graph without a stretch. So the a value is going to be 1 here. So I can just write square root of x minus 1. Again, that's because the h I know is 0. The k is -1, and the a value will be also 1, so no vertical stretch or compression. All right, let's keep it going with a couple more. Here we got more of our parent function graphs, so these get a little more interesting here, I think. Starting the same way. Again, looking at my transition, looks like it transitions at -1 on the x-axis. So my absolute value graph on the left is going to be x is less than or equal to -1, while my quadratic on the right is going to be x is greater than -1. So that's just saying, hey, there's my transition. I know it's going to switch from one graph to the other at -1. Include the closed circle. Do not include the open circle. All right, and now I got to go back to my parent function stuff. So let's see. This is an absolute value graph, and that point of it is my, it gives me my h and k. So that's -3, -1. And I can see that, again, there's no stretch or compression going on here. So I'm going to go ahead and just write the equation. Shifted left 3, so remember h lies, and then down 1. My quadratic, I see right away what jumps out to me. I can only see part of it, but I can tell clearly that quadratic is opening down. So with my vertex being right here at 0, 5, again, my h and my k, just like my h and my k was here, I know that's going to be x squared plus 5. And don't forget what I originally said. That's going to clearly open down. So again, I can choose another point on the graph and plug in that coordinate point of 1, 4 to transformational form. And it would look something like this. No, I have the x. The x is 1. And if I solve that out, that would pretty quickly actually just get me. This is plugging in 1 for x, 4 for y, 0 for h, 5 for k, and solving for a. That's going to get me an a value of -1. So don't forget negative in front there. All right, let's keep it rolling. Okay, now again, what do I have? I got a line on the left, and I have a cubic function on the right. So let's see, where's that transition? That transition looks like it's at -2. That's where it changes over. So my first equation is going to happen for x is less than -2. The second equation is going to happen for x is greater than or equal to -2. I did the same color, but that's okay. We're getting there. This line to the left here, I see again, it's going to be slope-intercept form. The slope appears to be up 1 over 1, up 1 over 1. So that's just x. So again, this is, if you get a line, think about y equals mx plus b. Y-intercept, I have to continue to line up and see what it is going to hit. It's going to hit at 4. So I'm going to say just x plus 4. Then the second piece of the graph, we'll go blue. Yeah, we'll go green. Is a cubic. And a cubic's HK value is at -1, -1, because it's the point of inflection. That's what's moved. The point of inflection is where it kind of flattens out there. So this is going to give me x plus 1, the quantity cubed, minus 1. And then I got to think, is there an a value? I could plug in this coordinate point, 0, 0. Or I could just realize that's going to be an a value of 1. We haven't hit any a values yet, really, besides -1 on that number 3. So that's my equation. All right, one more, guys. We're doing great. Oh, baby, we're getting to 3. 3 graphs. All right, let's go for it. It's all the same process. First chunk of this graph is a line. So I'm going to graph this guy here first. I see I can count the slope as rise 2, run 1, so 2x. And then I got to think where, if I continue that slope, that's going to hit at 3. So 2x plus 3. And that's going to be for x is less than or equal to -2. Next piece is an absolute value function. This is an absolute value function with the HK value here at 0, 2. I see no vertical stretch going on here, so I'm going to go with absolute value of x plus 2. And now this absolute value function is bounded on both sides. So I'm going to say essentially between -2 and +2. The x is in the middle. Not including -2, but yes, including +2. And this is just saying x is greater than -2, but less than or equal to +2. Final piece of this graph is going to be at 3, -1. Sorry, it's a quadratic with a vertex at 3, -1. So I'm going to start off by saying, all right, x minus 3 quantity squared minus 1. And that's when x is greater than 2. Don't forget your a value. This one does look like it's being stretched. And I can use either the shortcut method, or I can plug in the coordinate point for 1 as an x, y values. I would get an a value of 2. All right, last one. I suggest you pause this real quick and give this one a try. I'm going to do this one pretty quickly, so go ahead and pause it and try it for yourself. In the meantime, I'm just going to fill it out. All right, and there is your answer for this final graph. You've got a constant function, a linear function, and then a quadratic. Notice how the quadratic there is opening down. We can only see half of it, but I can tell that is a quadratic function. All right, great job, guys. You got your homework for tonight. Some more practice of this stuff. Keep up the good work.